This is part 2 on how to name inorganic compounds. In part 1, we reviewed how to tell whether an element tends to give away electrons or to grab electrons, and what kind of charge they would have, whether it be positive 1, plus 2, negative 1, negative 2, or some variable amount. We also looked at the idea of what a polyatomic ion is, and how to name those polyatomic ions if you have access to a polyatomic ion chart, something that might look like this right here, where you have the names and the polyatomic ions. Remember, polyatomic ions are more than one atom hooked together, and they have a charge of either negative or positive. They're not neutral. We also learned how to write out a chemical formula, and chemical formulas, of a compounds are neutral, and so we have to respect that fact by making sure that the charges all add up to 0. Okay. There are basically, I'd say, about 6 different types of naming systems within the inorganic nomenclature method. So that's kind of interesting that we have about 6 of those. I'm just going to briefly put up a little flow chart here. This is a flow chart for naming inorganic compounds, and we can just count them out. Okay, we have one naming system right here. Okay, that's if no metal is present. We also have if a metal is present in the compound, we have a very basic naming method. I can just write that here. And then, of course, if there's a transition metal which might have a variable, positive charge, then we have a third naming system we have to use. So there's 3 there. If we have a polyatomic ion present, we have to include that. I guess we could say that's the 4th method. We have to write the name of the polyatomic ion somewhere in that chemical formula name. And then if we have if we have a compound which is an acid, then we have 2 different ways of naming acids. We have this method here if there's no oxygen, and this method here if the acid contains an oxygen in it. Okay, so the inorganic naming system breaks down into 6 sub-naming systems, basically. And we'll get to each one of those in a bit. And you'll be able to use a flowchart if you need to, but most people find they don't even need to use a flowchart when they're naming. Okay, now I'd like you to get a detailed periodic table, one that looks like this from your notebook at this time. Looks something like this. And I'd also like you to get a polyatomic ion chart that you were given, something that looks like this. I'd like you to have both of them out at this point, get them from your notebook, and have them ready, because I'm going to ask you to do some work in a little bit. So have those out to refer to. Okay. The first thing I'd like to do is see if you can recognize whether a chemical formula has a polyatomic ion in it. So this is just a little exercise here. We'll do the first couple together, and then I'll give you a chance to work on a few yourself. Let's take a look at the first compound, CaCl2. Is there a polyatomic ion present? How would we know? Well, remember, poly means many atoms hooked together to form an ion. We see the calcium here. That's just an element, right? Ca. And we see that there are 2 chlorines, just elements. So the answer to that is there a polyatomic ion present? No. How about the second one? Here we have CO, which is cobalt, and then we have in parentheses NO3, and that little 3 next to it means 3 of whatever is inside the parentheses. Is there a polyatomic ion present? Well, the chemical formula looks complicated, so it could be so, huh? It could be. Let's check it out and see. Can we find a polyatomic ion that matches anything in there? So we'll just scan. NO3 maybe? Let's check it out. Oh, there's one. There it is. NO3. That's a nitrate, isn't it? So yes, there is a polyatomic ion present. And what's it called? It's called a nitrate ion. Let's check the third one out. KOH. Doesn't look that complicated. K is just potassium, O is hydrogen, and O is oxygen, H is hydrogen. But let's just check and make sure. So I look down on my list. Oh, there's an OH. It's called a hydroxide. So yeah, this OH right here is a polyatomic ion. And it's called a hydroxide ion. Well, that's how it's done. What I'd like you to do now is go down the list, stop your video, go down the list and answer the rest of these, and then turn on your video after you get done and see what the answers are. Okay. Okay, so here are the answers to the rest of these. For number 4, no polyatomic ion present. You might have thought maybe yes, because it looked like this one, but it's not exactly like that one, is it? It's CO2, and I don't see CO2 on here. CO3 with a -2 charge is a carbonate ion. That is a polyatomic ion, but CO2 is just a neutral compound, carbon dioxide. How about number 5? Number 5, we see this NO3 again. And remember what that is by this point? It's a nitrate ion. So yes, nitrate. Not nitrite, nitrate. Polyatomic ion here? No. It's just a neutral compound. How about this one? Number 7, yes. We see a CO3. Oops, I forgot to write no there. For number 7, yes. That's CO3. That is a, where is it again? Can we find it? Where's CO3? I'm looking. Can you find it? There it is. CO3 has a -2 charge as a carbonate. How about this next one? No. Just phosphorus and chlorines hooked together as a neutral compound. How about this one? CuSO4. Yes. The SO4, if we look down, that's a sulfate. How about this one? Ooh, it looks complicated, so there must be a polyatomic ion in here. Let's see. Well, there's a CO3. Would that be it? Is there anything else that we could have besides that? Ooh, there's an HCO3. That's even better, huh? So HCO3, that's known as a hydrogen carbonate ion, also known as a bicarbonate ion. So yes, that's a hydrogen carbonate ion. How about BRF5? No. H2SO3? Ooh, there's an SO3. Yes. SO3, what is that? That's a sulfite ion. Sulfite. ITE ending, as opposed to ATE for this previous one up here. NH3? No. There's an NH4 plus. That's an ammonium ion, but NH3 is just a neutral ammonia chemical, ammonium compound. H2S? No. TiCl3? No. Okay, so you've practiced looking at chemical formulas and trying to see if that chemical formula contains one or more polyatomic ions. That's an important skill to be able to have if you want to be successful in naming inorganic compounds. You need to be able to identify polyatomic ions. And the little memory helper is that most chemicals with polyatomic ions in them look a little more complicated than others. So that might be a help. Okay. Well, let's take a look at a type of naming system within that does not have any metals. And remember that the metals are to the left of the staircase on the periodic table. So anything to the left of the staircase is a metal, not counting hydrogen, but it still gives away one electron. The ones to the right of the staircase are nonmetals. So let's just look at the little variation of the inorganic naming system that only deals with nonmetals. Okay, so nonmetals in a compound. So only nonmetals in a compound. How do we name those? Naming. Okay, well, let's take an example. Let's look at something very familiar to us, like CO2. We already know that, don't we? It's carbon dioxide. And we are naming it correctly. Okay. This type of naming system uses what I call the mono-di-tri naming system. Okay. Mono means one. Di means two. Tri, three. Tetra, four. Penta, five. Hexa, six. Hept, 7, oct, 8, non, 9, dec, 10. Is that going to help us out? Well, let's see. Those are prefixes that we use in this naming system where nonmetals hook together. In the case of this one here, if we were to follow the rules exactly, we would call this monocarbon diox, and then instead of putting the whole word down, you just use an IDE ending. So monocarbon dioxide. However, for the first term, we eliminate the mono. That's the rule. And you write down carbon dioxide. Okay. Let's try another one. What if we had something like NO2? Do the same thing. Don't put mono in front because it's the first term. So you just write nitrogen dioxide. Okay, what if we have another one, but this time, what if it has sulfur in it or something like that? Like CS2. Well, that'd be carbon disulfide. See how that works? Remember, do not put mono if that's on the first term. Mono is understood to be there for the first term. If it's the second term, then use mono. Okay? What if we have something like, let's see here, something with one oxygen, like nitrogen monoxide. We'd write, instead of mononitrogen, we'd write nitrogen. Since there's only one oxygen here, we'd write monoxide. Now, I know it says mono, but we don't want to put two O's next to each other. We just make a contraction and write it monoxide. So nitrogen monoxide. What if we have something like this? N2O4. Well, then that'd be dinitrogen, and then 4 is tetraoxide. And you can even make a contraction for that and put tetroxide. But if you put tetraoxide, that would be fine too. Okay, so that's the first type of naming skill you need. And this deals with compounds that only contain nonmetals. Compounds that only contain nonmetals. Okay? Now you try a couple. Ready? P3O5. How about another one? Such as SiO2. How about another one? OF2. Okay, stop the video and answer these, and then come back and we'll go over them together. Okay. Well, remember, 5 is what? 5 is penta. So, and 3 is tri. So we'd write down triphosphorus penta oxide. But instead of putting the there, I just make a contraction and put pentoxide. So triphosphorus pentoxide. How about the next one? We look up Si on the periodic table. That's silicon. And we have 2 oxygens, so we use the prefix di. And we then put oxide. The next one, we have monooxygen, but remember we'll just write oxygen there. And then, because we don't use mono for the first term, and then we use difluoride. So oxygen difluoride. So good. That's the first type of naming system, and that deals with naming compounds that only contain nonmetals. Okay. The next type of naming system contains metals and nonmetals. Metals and nonmetals. So let's look at those. Okay, some examples would be NaCl. The first term is always the metal, and the second term is the non-metal. How would we name this? Well, we use the most basic naming system of all. We just write the name of the metal, which in this case is sodium, if you look it up on the periodic table, and we write the first part of the nonmetal, which would be chlor, and then put an IDE ending. So the name is sodium chloride. So if you have just a simple metal hooked onto a nonmetal, you just write the name of the first element, which would be the metal, and the stem of the second, the nonmetal, and then put an IDE ending. Let's try a few more. Okay, what if we have something like MgF2? Ooh, that looks a little more complicated, but really it's not bad. We write the name of the metal, magnesium, just look it up on the periodic table, and then you write the stem of the nonmetal, which should be fluor, from fluoride, and then put an IDE ending after that, so magnesium fluoride. How about another one? How about Na2, Na2O. Write the name of the metal, which is sodium, and write the name of the nonmetal, the first part of it at least, ox, and then put an IDE ending, so sodium oxide. Notice that I don't even have to incorporate the little subscripts like I did in the first naming system for nonmetal nonmetals. For metal nonmetal, you don't have to incorporate the little subscripts in. We don't have to put di. In fact, don't do it. It'd be wrong. So it's not magnesium difluoride here, is it? It's magnesium fluoride. However, if it was two nonmetals being hooked together, we would incorporate the word di in there for that one. So that's the second type of naming system. That's one where you have a simple metal hooked on to a non-metal. Third type of naming system deals with a metal, but the metal has more than one possible charge. So this would be a metal with more than one possible charge hooked on to a non-metal. Okay, if we look at the periodic table, we'll look at a very detailed one here. We can see, for example, iron. Iron has two possible charges. This one isn't showing up very well on the document camera, but if you look at your own, you'll see it has a +2 or a +3 that it could have, one or the other for iron. We see copper could be a +2 or a +1. We see nickel could be a +2 or a +3. We see titanium could be a +4 or a +3. So that adds a little bit of complication, because there could be more than one possible name. Like, say for example, what if you were working for a scientist, and the scientist asked you to go into the chemical storeroom and get some iron oxide for her. Okay, iron oxide. So you go in there and you see that there are 2 jars in that section, and one has the chemical formula of FeO. That's in one jar, so let's say there's the jar. And the other jar has Fe2O3. There's a little cork sticking out of it. Okay, so you bring them both out and you go, okay, well, which one did you want? And the scientist might then say, oh, okay, yeah, I needed to be more specific. So I should have said iron 3 oxide. Iron Roman numeral 3 oxide. And that would have told you which one of those to use. Which one of those would that have been? Well, if we look at this one here, if we analyze the chemical formula, we have 2 iron atoms and we have 3 oxygen atoms. Excuse me, let me get the light back on. Nothing like automatic lights. Now, remember that oxygen has a -2 charge when it forms an ion. So we have 3 of those at -2 apiece. That adds up to a -6. We have 2 irons. What should those have? Well, if we have 2 of those at +3 apiece, that would add up to a +6. A +6 and a -6 would neutralize each other. So it must be that an iron 3, that this has iron 3 ions in it, because each iron ion has a +3 charge. So iron Roman numeral 3 ions are in, that's an iron 3 ion right there, that Fe+3. So that must mean that this is the one she wanted. This is the compound she really wanted you to get out of the chemical storage room. She wanted the one with the iron 3 ions. Iron 3 oxide. Well, what would this other one be called then? So this is iron 3 oxide right here. What would this one be called? Well, let's look. We have 1 iron ion hooked onto 1 oxygen ion. Oxygen, of course, always or almost always has a -2 charge when it forms an ion. And then this 1 iron hooked onto it must then in turn be a +2. So what would we call that? We'd call this one iron Roman numeral 2 oxide. So now you can see the reasoning of why, if we have metals with more than 1 possible charge, we need to be very specific and use a Roman numeral to indicate what that charge is. So iron 3 indicates that the iron ion has a +3 charge. The iron 2 part of the iron 2 oxide word indicates that the iron ion in this compound has a +2 charge. Without the Roman numerals, we wouldn't know. It'd be too ambiguous. Okay, time for some practice. How about this one? CuSO4. So we'll look at your periodic table. We look at copper. It could be a +2 or a +1. Could be a +2 or a +1. Which one is it? Well, if we look at the SO4, that's a polyatomic ion. What's its charge? So we look at SO4, has a -2 charge. For the SO4, that must mean then that the copper has a +2 charge, because there's 1 copper for every 1 SO4. So then this would be copper Roman numeral 2, since it has a +2 charge, and then we'd write the name of the polyatomic ion, which would be the sulfate. So copper 2 sulfate is the name of this compound. How about something like TiO2? TiO2. That'd be a good one? I'm checking here. Or TiO. Yeah, that would be good. Okay, so what would we name? How would we name that? Well, this is a metal, so we can't just say something dioxide, right? We can't do that. We look at the periodic table and we notice that titanium has more than one possible charge. It could be a +4 or a +3 charged ion. It depends on the situation. So we look at, we see that oxygen here. Oxygen always has a -2 charge, but there's 2 of them at -2 apiece. So -2 charge times 2 oxygen ions, that gives us a -4 total for the 2 oxygens. That must mean that the titanium must have a +4 because there's only a single titanium ion there. So we'd write that out as titanium, Roman numeral 4, and then we'd write the word oxide after it. So that's how to do it. Okay? So we've basically shown you how to name a chemical that contains a metal with more than one possible charge onto a non-metal, and I also showed you how to incorporate that with a metal with a polyatomic ion. Okay? So this is the end of part 2, and we will go to part 3 next time. Thank you very much.